Okay, so this is the third lesson in our toxins unit. And we're going to be talking about chemical versus physical change. Oops. So when you have a physical change, it's a change in matter. So these are all changes in matter we're talking about. Change in matter in which a substance changes form but not identity. So really the key idea here is that no bonds are made or broken. So you're not breaking any metallic, ionic, or covalent bonds during a physical change. And a chemical change is a change in matter that results in the formation stop. How do I stop you? Okay. In the formation of a new substance with new chemical properties. Now, to bring you back to this idea of a chemical change, oh, so one more thing. The way atoms are bonded changes. Now, we haven't done much of this during the year, but one example of when we did this was when if you remember, we took that thing that smelled like dirty feet or really rotten cheese and reacted it with something else, and then it made a sweet smell. So in that case, the chemical properties changed. In this case, the smell. The smell of the substance changed after the chemical change or chemical reaction. And a physical change really, going back up here for a second, it's really disrupting intermolecular forces, separating or joining them. That tends to be what we think of when we think of physical change. So CO2 solid to CO2 gas. This is something you saw the other day when we were doing the dry ice. So in this case, we think to ourselves, were any bonds made or broken? Well, we start with CO2 solid, we end with CO2 gas. The way the atoms are bonded to each other stay the same. The only difference is we're going from a solid. So what this is called is this is a particulate representation. And I really love these. They're kind of annoying for you guys, I understand, but they really help you understand what's going on at the atomic and molecular level. We have CO2. First thing we want to think about is what type of bonding is present in CO2. So I think to myself, okay, carbon, non-metal. I'm looking at the periodic table. Oxygen, also non-metal. So I have non-metals bonded together. So that means it's a covalent bond. And if you do out the Lewis dot structure, you'll find it's a double bond. So solid CO2, we have these molecules of carbon dioxide that it's cold enough such that their intermolecular forces can hold them together as a solid. I'll just draw like one more. Another question would be, what are the most important intermolecular forces present in CO2? Well, CO2, if I look at the Lewis dot structure, I get this. And I do know that oxygen's more electronegative than carbon. So I know I have polar bonds. But then I look at the shape. What's that shape? Oh, that shape is linear, right? There's only two domains, linear. So this molecule is symmetric, or symmetrical. So any molecule that's symmetrical has dispersion forces as its most important intermolecular force. Pretty weak, but if we cool it down low enough, then it'll be a solid. So now we add heat, and it becomes a gas. Well, those molecules stick together. The difference is now they're just not right next to one another. Whoops, that's an O right there. They're free to move all about the container. I'm assuming this container is closed. I should close this container. So, key ideas here. I have the same number of atoms on both sides. I haven't changed what's bonded to what. I've just disrupted the intermolecular forces. And we'll do a lot more of these. Oops, that shouldn't be there. All right. So S plus O2 becomes SO2. All right. So we start with, we look, okay, sulfur and oxygen makes SO2. Well, now I have a chemical change. This is definitely a chemical change. So I start with two different things. S is a nonmetal. So the individual S atoms are covalently bonded together. What you guys don't need to know is, oops, that's a backwards S. And let's just do 3 of them they're covalently bonded together. You don't have to know how. They're sort of this long. It's not network covalent, but they do bond with each other in a specific arrangement. And then we'll do 3 O2 molecules. These are gases now. And so when I put them together, I have SO2 gas. And we get, excuse me, 3 SO2s. Okay. So here I'm actually seeing that bonds are being broken. The bonds here are broken. These bonds are broken. And I get these bonds being made here. All right. So bonds are broken, bonds are made. The next two we're going to do in class. They're a little tricky. I want to do those together. So it's not always possible to distinguish between a physical and chemical chains based on observations alone. So let's do, we have this, for example. Now, sometimes observations alone are insufficient to determine if a change is chemical or physical. I know when you were in middle school, they would say, oh, a color change means that a reaction has happened. Well, in this case, with COCl2 solid dissolving in water, you actually do get a color change. But this is a very subtle, or subtle is not the right word. It's hard to distinguish whether or not this is a chemical or physical change. So, dissolving substances in water is neither chemical or physical exactly. It doesn't really fit into either category perfectly because you are breaking ionic bonds in this case. But if you boil off the water, you'd get the same thing right back. So you're not really changing the properties so much. So anytime you have something dissolved in water, it's neither chemical nor physical exactly. Historically, it's been a physical change has been what it's categorized as. I'm not going to ask that of you. Just know that there's some subtlety, there's some nuance, and it's a continuum of chemical to physical change. Okay. So ionic compounds, we're going back a little bit. This is a longer lecture, but ionic compounds don't dissolve in the same way as molecules. So they split into ions. This is what makes it extra tricky to determine whether or not it's a physical or chemical change. So if we look back to that last chemical equation with cobalt chloride dissolving, we could also write it this way. I think the way I had it written before was this. Either one is okay. They mean the same thing. The one on the top is a little bit more specific, but it makes it look like a chemical change. The one at the bottom makes it look like a physical change. Oops, I'll write that in. Looks like chemical change. Looks like physical change. All right. So I left that. This is from Mr. Hamill's slide last year. I left that one in. How are changes in matter classified? Well, chemical changes involve the formation of new substances. That's what the sort of definition. Physical changes involve a change in form, not resulting in new molecule or new substances. I mean, dissolving generally is considered a physical change, but it has something in common with chemical changes as well. We've been looking at chemical equations, and they often provide more straightforward information about the type of change more than mere observation. So if you look at the chemical equation, you're going to get more information than you would just from observing the change in the lab. And those particle drawings, the particulate representations, they give even more detailed info. That's why I really like them. They take a chemical equation and really visualize what's going on at the atomic level.